It was just 4 years after the Soviet Union had launched Sputnik.
Today, a new moon is in the sky, a 23-inch metal sphere placed in orbit by a Russian rocket.
And the space race was ramping up into full gear. The first weather satellite, launched on April 1st, 1960, Tyros 1, enabled us to see weather, at least in the form of cloud cover, across the globe. For the first time, we could see today's weather from space, which provided clues about what tomorrow had in store. With each passing year, we gained more confidence in our weather forecasts, compulsively checking out the hourly forecast before heading out the door, or scanning weather radar in real time, or eyeing the 10-day outlook for next weekend's plans. Our ability to predict the weather, though still imperfect, would astound our recent ancestors. But not that long ago, weather forecasts were much, much murkier, and recent improvements have made revolutionary contributions to not just picnics and daily commutes, but farming, worldwide economics, construction projects, military strategy, and travel by air and sea. We talked to pioneers in the field who in some cases have lived the lion's share of the history of modern weather forecasting. Out of that, we want to share 5 things, mostly from the US satellite era, that changed forecasting forever. But first, we'll start a little further back into the past.
Throughout the history of what is now the National Weather Service, threats to life has been one of the main drivers for us to even exist. The initial organization that started weather services in the United States was the Signal Corps, which took on the responsibilities to observe weather and be able to provide indications of what could happen that afternoon or the next day.
After the Civil War, the Great Lakes were a main highway for commerce, and ships frequently sank in surprise storms.
Telegraph lines made it possible to get weather information in real time that could all be brought together to provide indications of squalls passing over the lakes. And so that's the creation of the Signal Corps. Then you move forward in time. In 1888, for example, there were 2 major blizzards that affected the United States.
These blizzards were barely forecast, and hundreds of people lost their lives.
There was a general push to get the weather services out of the military Signal Corps into a civilian agency, and that was probably the last straw for many of those who really wanted this to happen, and it became much more emphatic.
Then the weather disasters of the 1900s, like the surprise Long Island Express hurricane in 1938 and a major tornado outbreak in 1974, spurred interest in new technologies like Doppler radar that could give a local or regional view of developing weather. But it was really the view from on high that brought the world's weather forecasts together. Not many people know that during John F. Kennedy's famous speech to Congress in 1961, he not only set this audacious goal.
First, I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
He also called out for the development of a nuclear rocket and a worldwide system of communications satellites, and
fourth, an additional $75 million, of which $53 million is for the Weather Bureau, will help give us at the earliest possible time a satellite system for worldwide weather observation.
Tyros 1 and 2 had already launched before the Kennedy speech, but a long series of Tyros satellites followed after, which were then complemented by the Nimbus program, a set of satellites designed not just to take pictures, but to actually measure aspects of the atmosphere from hundreds of miles away, including temperature, wind speed, and water vapor. Scientific progress is often slow, building incrementally. But sometimes science makes giant leaps, literally overnight. For the field of weather forecasting, this happened one night in 1969, just 3 months before the first humans landed on the moon. It was the night the team behind the Nimbus 3 satellite received their first global set of data.
We stayed up all night and plotted these data on a map, hand plotted them. We got the computer, just reams of paper with numbers on them, latitude, longitude, temperature values, altitude and things. It was pretty exciting because it looked very real, just like a real weather map, but this just came from the satellite. Nothing else, just the satellite data.
When morning came, they brought their weather map to the Director of Operations of the National Meteorological Center.
He says, "Oh my God, we've been taking flack from the airlines this morning because we misforecast where the jet stream was going to be. And our flights to Asia we're not making their destination because of strong headwinds and so on that we didn't forecast." And he says, "And your satellite data shows right where it is."
The Tyros and Nimbus satellites and other low-orbit satellites that followed circle round the Earth, getting different views all the time. But now let's talk about the view from 10 times higher up.
The geostationary program has primarily been a visual imagery program. It's basically flying above the equator at the same rate as the Earth spins, so to a person on the Earth it appears that it's stationary. And what that allows you to do is see the Earth from the same vantage points continuously. So you can basically take movies, so you can update the picture every 30 seconds if you want. When you loop those, you get a sense of the motion of the weather.
We forget the days where the TV folks who were talking about a storm being out in the Atlantic couldn't even show where it was, just that the Hurricane Center is tracking it. Papers have been written about how the geostationary satellite was probably the most important observing system with its ground processing in the history of advancing the Hurricane Center, because it gave them the situational awareness of where that storm was, where it was going, and the intensity changes as it was moving in real time. It was just an amazing, eye-opening experience for the Hurricane Center.
So, geostationary satellites give us, literally, the big picture. But from a data standpoint, it's usually been the low-orbit satellites, usually in a polar orbit, that are the workhorses of the weather fleet.
The polar orbiting satellites complement the geostationary, basically flying a little over 500 miles up. And when you're at that altitude, you can sense what's in the atmosphere to a lot higher resolution. And for weather forecasting, you really want to understand the state of the atmosphere, primarily temperature and water, vapor, and winds. Twice a day, each satellite is giving a really detailed measurement of the atmosphere and its state, which is the beginning then to understand what is the statement of the global atmosphere to then project it forward to produce a weather forecast.
The early Nimbus satellites began our legacy of low-orbit data collection, but one of the biggest leaps came from our ability to measure literally thousands of different frequencies of energy, representing an all-weather profile of the atmosphere. For NASA Goddard Space Flight Center's Ed Kim, that all-weather view is never far from his mind.
I have a vested interest in helping improve weather forecasts. The hobby of flying and the work of improving weather sensors is a nice combination. They really go hand in hand. When you're flying around and looking at clouds or looking at weather patterns as you're flying in an airplane, it's hard not to think about what a microwave sensor would see when it's trying to look through that cloud over there to the right. So everybody's probably familiar with radio transmissions. You have a transmitter, you have a receiver. Maybe when you were kids you played with walkie-talkies, or you listen to the radio in your car, there's a transmitter somewhere and the receiver's in your car. The microwave sounders are just the same thing, just different radio frequencies. So you might ask, well, what is the receiver receiving? It's actually receiving natural signals that are emitted by the gases in the atmosphere itself. All natural objects, everything emits very tiny amount of microwave energy. And those microwave frequencies happen to allow you to detect the condition of the atmosphere. And so then you can construct the vertical temperature, we call it a profile, a vertical temperature structure of the atmosphere. The primary reason that you have both the microwave and the infrared is that the microwave sensors in general, for the most part, can see through clouds. Just the fact that you could see through the clouds and still figure out the structure of the atmosphere was a gigantic leap forward. Combine the microwave data and the infrared data, provide that really critical vertical structure information of the atmosphere to the weather forecasters. Essentially the most critical information they need for weather forecasts.
So we have a non-stop visual recon of the planet from geostationary satellites and highly detailed atmospheric measurements from polar orbiters. But all that data coming down wouldn't mean much without the quantum leaps in computing power we've seen over this time period, and the massive amounts of work that have gone into creating computer models of weather and our atmosphere. One of the pioneers in this field is Eugenia Kalnay, who, after escaping a brutal crackdown on academia in Argentina, became the first woman to graduate from MIT in meteorology and has possibly the most often cited paper in all of the earth sciences. One of her major fields of study has been the ensemble forecast, basically comparing bits of forecast model information against each other to figure out what's working and what's not.
This method allows you to determine whether each observation is good or bad, if it helps the forecast or it makes it worse. And I realized that we could do that with every observation and determine whether it was beneficial or detrimental. We could take away the detrimental observations and only use the beneficial ones. And that has improved the forecast quite a lot, substantially. Not just a little bit that you cannot see, but for 8 days the forecast is better. So that I feel very happy about that result.
Before the ensemble, she says, the National Weather Service would calculate a forecast for 15 days, but only show 3 days to the public. But in the 1980s, we made a major leap.
That was the first time that the human forecasters there make a forecast for 5 days, and because they saw that all the ensemble forecasts were similar. The TV meteorologists immediately, the most advanced of them, immediately realized that they could give forecast much longer than 3 days.
So now we have the data, and we have the computers and the models to run on them. But that still doesn't do us any good if we can't get the data down from the satellites, processed, and then out to the people who need it.
We're sitting here at the NSOF building. It's really the operations center for all of our NOAA satellites. So behind me you can see the floor where not only do we fly the geostationary satellites, the polar orbiting satellites, including JPSS-1, which is now called NOAA 20. The primary purpose of this building then is to fly the satellites and then take the data from those satellites and process it and be able to put out the products for the nation. The data that flows from all of the satellites produces a lot of the products that are used in the weather forecasting that everybody sort of uses every day and may not really understand where it's coming from, but this is the heart and soul of what the nation gets for weather forecasting. So the nice thing about working in this business is we know it's helping people all over the world, and all the countries of the world collaborate very well together in sharing this data because it's all of mutual benefit.
But getting those forecasts out is still not the end of the line. In emergency weather situations, the right people have to get the right information to make critical decisions.
Well, one of the new areas that the Weather Service is fully engaged in is the idea that making a forecast and a warning is not good enough. And there's a whole range of decision makers. There's organized decision makers, government agencies at the federal, state, and local levels all work together to save lives and property. And then you got individuals. Everybody with a cell phone now is a decision maker. They can download all this stuff and decide whether they're going to evacuate or not, right? So we're into human factors now. We're into social science. So this combination of physical and social science is really a big deal for us in how we meet the needs of the emergency management community. If we all want to get down to societal benefits, this is what we've got to do. We've embarked on this over the last 6, 7, 8 years, and it's starting to work. The part of the mission to protect life and property is really the driver, what brings people to work every day, and we certainly are dedicated to that mission.